Okay, fine. So today we are going to discuss CFD lab part. Okay, we are going to solve the first problem. So this is the first problem which has been given in our lab cycle of CFD. CFD lab cycle. Bracket let me write as BMSC. Okay, so this is the uh, first problem. So they are given a model. Okay, so in this model, let me define what is this model properly. They are given a geometrical model which has a following dimensions. I'll show the dimension. So this is the dimension what we required for our problem, only this part. So this we are going to solve 2D plane problem. Okay, we are going to solve 2D plane problem. So we are going to take only this part. I'm going to consider only this part. I'm not going to consider the depth. Okay, so I'm going to consider only xy, neglecting the z direction. So I'm going to consider this as a 2D problem. So the dimension for this, okay, the dimension for this. So inlet, the dimension of the inlet is 0.5 meters. Length of the plane, length of the plane, the length of the plane. If I consider the length of the plane, it is 1.5 meter. Outlet dam, like outlet, it is 0.25. They are given in the problem statement. They given in the problem statement. Accordingly, I'm writing. So this dimension also, which is it is necessary. The tapered one. What is the distance between these two? It has been suggested that it should be 0.125 meter. So all dimensions are in meter basically. So we are not going to take the entire model. We're going to take a lamina. Lamina means which has only two dimension. Only this part we are going to consider. We're not going to consider the entire 3D model. Just a lamina I'm going to take. Just a lamina. Okay. And they are given some initial condition. I just want to highlight the initial condition. At inlet, the velocity of the inlet is 0.002263. There is a calculation for it. I'm not going to show the calculation. Instead of that, I'm going to take directly the inlet velocity. And the exit velocity we are not going to consider. Instead of that, in the problem statement, the boundary condition what they are given at exit, at outlet, we are going to take the pressure. This pressure, outlet pressure, we are going to consider as atmospheric pressure. But for an ideal case, we suggest that the outlet pressure will be 0 Newton per meter square. And we consider this wall surface. This is called the wall surface. Apart from inlet and outlet, the other surface it is called as a wall surface. The wall surface we treat them as an adiabatic wall. Adiabatic means there is no heat transfer, or we can also tell that there is no slip condition because there is no slip condition. So let me take that u of x,
Can you
u of
explain me
y.
once again about
So
that slip condition?
that is what I'm explaining. So only we are considering that there is an velocity flow only at the inlet, and we are just neglecting the wall velocity. We are just neglecting the wall velocity, that there is a free stream. There is no action of the velocity at the wall surface. That is called a no slip condition. You take a boundary layer at this point, what you will call u equals to 0, u of x is equals to, that is means no slip. Similarly, we consider there is no action of the velocity acting on the wall surface, no slip condition basically. So when I assign the boundary condition in our Fluent, then you will understand better. So we consider there is no action of you velocity at x, velocity at y. We just consider it as 0, which means no slip at the wall, and there is no heat extraction or like heat interaction. That also we are considering as 0. Only two things involved. One is inlet velocity, velocity at inlet. At exit, there is a pressure, that too 0, which means there is atmospheric pressure.
Okay. We will consider no slip during conditions like heat transfer is 0,
Yes,
and the other condition is like ux and uy is equal to 0.
yes. At wall
Okay, okay.
condition,
To
we
wall.
are
That means
considering at wall.
velocity will be 0 at the wall.
Yes, yeah. Because problem statement, they are clearly mentioned the boundary condition, like adiabatic wall, no slip condition means this condition should satisfy.
Okay.
Okay, so you understood the geometry how it is basically. Fine. So with these details, let me open the Ansys Fluent. So open Workbench. It takes time for loading. Okay. So this is our Ansys workbench. So in this workbench, you have many solvers, but we are only interested at the fluid flow. In this fluid flow, again there are many solvers, but again we are interested in one particular fluid flow, that is called as fluent. Fluent. So we are going to drag this fluent and drop here. Yeah, there are many fluid flows. In that, we are taking only the Ansys Fluent. That is nothing but fluid flow Fluent. So in this Fluent, you can see nearly six steps. Okay. So the Fluent, it is a first dialog box which is already opened. So second is geometry, which means you're going to create the like 2D models or 2D plane or 3D plane or 3D models. You're going to generally create the models. So that is the main intention of geometry. Next is meshing. So in meshing, what you're going to do is in meshing, you're going to give all the boundary condition and you're going to discretize the geometrical model into finite element. So meshing part and boundary condition you will be giving here. Okay. Once the boundary condition is given, next what you're going to do is you're going to set up. In this setup, you are going to give, once the meshing is done, in setup, what you're going to give is you're going to assign various values. For example, you're going to assign the velocity. You're going to assign what type of flow is happening. You're going to assign what type of like boundary condition you need to give. All those things you're going to assign here in setup. Once setup is done, like you're going for solution. In solution, what happens, you're going to calculate all the uh, meshed models, which already whatever boundary condition whatever you given, you're going to solve it mathematically. Once the solution is done, you can extract all the results. So these are the basic step. You're going to you're going to model it. After modeling, you're going to mesh it. After meshing, you're going to give the boundary condition. Once boundary condition is given, you're going to solve it by various iteration. Once solution is done, you're going to extract the results. These are the 6 steps you're going to uh, solve in the Fluent. So I'm going to start with the geometry part. If you open geometry part, there are various you can see the various options. In that, I'm going to choose the second option, new design modular geometry. New design modular geometry, and I'm going to open it. So basically, it takes time. Fine. Now our influent geometry part is opened. So now what you're going to do is you're going to create a model. You're going to create a model. So before that, let me see how is my model looks like. What are the dimension of my model? So basically, it is uh, a kind of trapezium which has a base of zero point 0.5 and base of like height of 0.25 the like other side, and the height of 1.5 meters. Basically, it's a kind of trapezium or a tapered bar, whatever it is. So at inlet it is zero point 0.5, at exit it is 0.25, and the height or length of the bar is 1.5. Actually, it's a 2D plane. Okay, let me draw this. How to draw this? See, in this you have an option called as sketching. Sketching, just click on sketching. Okay, before sketching, let me choose my plane, in which plane my fluent should work, or in which plane my geometry should be assigned. So if I carefully see the sketch, like it is in which plane? It is in XY plane. Basically, this is the x-axis and this is a y-axis. So I should write in xy plane. I should draw my drawing in xy plane. So how I am going to set this plane means, can you see this? At the bottom right corner, you see a coordinating axis. In that, you just click on Z, because Z is normal to XY plane. If you click that, your XY plane in 2D format it comes. Okay, at bottom right corner, I just clicked on Z plane, so your coordinate or your plane is ready for sketching. Once this is ready, go for sketching in sketching toolbox. Sketching, first you go for constraint, coincident. Why I choose in the, like instead of drawing, why I am choosing this means, because the geometry looks something like this. This should coincide with respect to this. So to build a relationship, first I am using those options. I'm going to draw line. I'm going to draw it. So basically, I'm going to draw roughly. I'm not going to give any dimensions. Later, I can assign the dimension, but let me draw it roughly, like how our model looks. So this is what our model. It looks something like this. Now I'm going to dimensions. In this, there are a lot of options. It starts from general, horizontal, vertical. But currently, I use horizontal and vertical. So horizontal, I'm going to build a relationship between these two. Okay, let me draw a vertical. Yeah, let me use vertical. Yes, I can establish the relation or dimensions. Horizontal. And finally, yes. So these are the dimension I have given. Like I need to assign those values now. How I am going to assign means here you have detailed view. Detailed view. In this, you have this option H4 in dimensions H4, V2, V3, V5. It is nothing but these values. So I'm going to edit here. Okay. So before that, make sure our units are in meters. If you change the units, things will change. So make sure it is in units. This is in degree. So H4 1.5, 0.25, 0.125, 0.5. So I have given the dimensions. Let me zoom and show you. Now it is properly assigned. It is properly assigned as per the given sketch. So once the dimension is done, you need to give generate. Suppose if you forget to give generate, the Fluent doesn't remember what the value you have been assigned. Once giving the generate, our model is done. You can see the tick mark, the model is done. Fine. Now next what we're going to do is, next what we going to do is, so once the sketch is done, we need to prepare the plane. Actually, this is a line diagram. It's not a surface. It doesn't have any plane. So it's just a line. We just connected those lines. Now we are going to model, or we are going to make it as a laminar or plane. So in that, what you're going to do is you're going to go for concept, surface from sketch. Then you're going to select the plane and you're going to apply it and generate. Surface sketch one, apply, generate. So our lamina has been created. Now what we are going to do? Now we are going to give the boundary condition in geometry itself. We are not going to assign any value, but we are going to tell the Fluent these are my boundary conditions. So what we're going to do is we're going to select this option, select filter edge, and I'm going to click here, right click, named section. Can you tell me what is this exactly? This particular thing?
Inlet.
Very good. So we are going to name this as inlet. Inlet. So we have selected this particular thing as an inlet or this particular edge as inlet. How many edge it is? It is one edge. We have selected and I am going to enter it. See, unless and until if you give generate, your Fluent will not understand what is happening. See, it's like a symbol. This symbol you can see, no, when you see the symbol, it is not saved. If I give generate, you can see the tick mark, which means it has been saved. Now I'm going to assign outlet. I'm going to select the same outlet, right click, named section. What I'm going to type here, outlet. Now what I should do? What I should do?
Generate.
Yeah. Now it's saved. Similarly, I have given inlet and outlet, but I have not assigned wall. Now I'm going to assign wall also. So to assign wall, you should click on control and select both the faces, both side of the wall. See there is a change in green color. Now click right click, named section. I'm going to call this as wall and generate. So basically what and all things I have done, let me tell you in brief. First I have just drawn a line and randomly gave the dimensions, and after dimensioning I have entered the exact dimensions what we want. After entering the dimension, I went to concept, surface from the edge I have taken, sorry, surface from sketches I have taken, and I selected the respective sketch and I prepared a plane. After preparing a plane, what I have done is I assigned which should be the inlet, which should be the outlet, what is the wall. So these things I have assigned in the Fluent and I have generated it. So this is all about the geometrical part. If you have any doubt, you can ask.
No.
Okay. So just click and make sure at inlet one edge, at outlet one edge, at wall how many edges should be?
2.
Two. So whatever we have done it is said to be correct. So I'm going to close the modeling part. When you click on generate, it is understood that your whatever the problem you have solved, it has been saved in your Fluent. Now I'm going to close it. And I'm going to open the workbench. See. Can you see that there is a tick mark? It has been generated, which means my modeling is said to be done. Now I'm going to open with machine. Basically, it takes time. We need to have a lot of patience. This is our model. Now again, I'm going to make it as 2D plane. I'm going to press the Z, which is at bottom right corner. This is our model. Now I'm going to give the inlet condition. I'm going to give the inlet condition, or I'm going to mesh the inlet, outlet and wall. All I'm going to do is in project, in project, in project, I have mesh option. I'm going to right click it. I'm going to select sizing. Click it. Okay. Once I click this sizing, you will get a pointer something like this. When you click near the walls, it shows. So you're going to click on the edge, click it, apply it. You'll get something like this. I'm just meshing the inlet. Now what I'm going to do is, this meshing is a random mesh, but I want it to be meshed in proper size. So what I'm going to do is, I'm going to go for element size, sorry, type element size. In that I'm going to give number of division. So in number of division, I am going to take as 50. You can give 100,000, whatever you want. If you keep on increasing the mesh size, your computational time will be taken more. So I'm taking randomly as 50 and I'm going to enter it. So at inlet, I have been meshed. So I have divided this inlet into 50 parts. Same procedure I'm going to use. Mesh, inlet, sizing, corner, apply. So I am going to give how much number of division, how much I am going to give. Basically, let me show it in a broader way so that you can able to see 50. It is meshed. Okay. Next, I am going to mesh this by pressing Control, apply. Here, what I'm going to do is, since the length is too much, I'm going to give 150. I'm going to give this 150. So generate. How beautifully it has been meshed. But it takes time. Now the proper meshing is done. So see this. When you closely observe this, at the border it has been finely meshed, but at center it is not meshed finely. So in Fluent it will not take something like this. At border it is properly meshed and at face it is not meshed properly. So Fluent will not solve. So what we're going to do is we are going to mesh it. There is called as phase meshing. I'm going to click that. I'm going to click the entire phase, apply, generate. Can you make out the difference? See how it is meshed. Let me show in see how fine it is meshed. Generated. So now the meshing is done. So once the meshing is done, I'm going to close mesh. See, can you observe one thing? What do you observe? Geometry part is done, but mesh part, it's showing it is not completed. So in that case, what you're going to do is right click, click on update. Meshing is done. So once you see the tick mark, then only you can proceed to the next steps. So now I'm going to set up. Hmm. You will get a Fluent launcher. So as we suggested, this diagram is a 2D diagram. So by default, it is a 2D. Here I am going to use double precision, display mesh after reading and double precision. These two dialog box should be tick and I'm going to start it. So it takes time to open all the dialog box, close all the things, and this is very important. So you're going to solve everything in here. So here there are a lot of options. You have setup, solution, result, all those things. So in this you're going to start with the general, setup general. In general, what type of problem it is? It is a pressure based problem. Okay, basically when you solve the velocity type, like which is involved velocity, it is absolute velocity, and basically it is a pressure type problem. Where you're going to use density based problem is density based problem we use in natural convection. If it is not a natural convection, we are going to use only pressure type of problem. And what type of problem? It is a steady or transient. What type of problem it is?
Enjoying.
Steady.
Yeah.
It's a steady type of problem. It is not a transient. It is a steady type. Okay. Just remember, because there is a calculation and we found it has to be a laminar flow. So it is a steady type problem. It is a pressure based. Velocity is absolute and it is a steady. Okay, when there is a natural convection problem, there you're going to use relative velocity, or else like it is a natural velocity. And what type of problem it is? 2D planar problem. Planar means it should be what? It is a 2D problem. A symmetric problem means which has a symmetrical dimension. Symmetrical swivel problem means which has something like circular cross section, those things. And down you see the gravity. Okay, this gravity should be ticked when it is a natural convection problem, or else it should be unticked. Okay. In general, these things you need to know. In solver, what type of problem you are using is pressure type, absolute, steady, 2D planar, and the gravity should be off. So next, in model, in model if you see, there are many types: multiphase, energy, viscous, radiation, heat exchanger, species, discrete phase, all those things here. So in this, based on the type, we are going to select. Okay, so basically, what type of problem it is? It's just a flow problem and viscous type of problem. So here we are not using any energy, or in no heat transfer is taking place. Only the viscous force acting here. So we're going to select viscous force. If you open viscous force, there is a inviscid, absolutely no viscosity, laminar. Apart from that, all the things are turbulent. K epsilon, K omega, this is an all turbulent type of flow. So our problem is a laminar type of problem. So I'm going to click laminar and give OK. See, when I do that, only viscous it is being converted to laminar. Only viscous option is on. Rest other option it is off. So we should be very much careful that all the other option is off. Only the viscous laminar should be on. Which means if any other option is on, what happens means our computational time, apart from viscosity, if I switch on heat exchanger, it will compute both heat exchanging thing and viscous thing. So the computational time will be more. So as far as a problem is concerned, it is a laminar type of problem. I selected laminar and I closed. All other option is set to be off. Okay. Now I'm going to material. So in this problem, let me open the real problem statement. What is the type of flow is considering water is flowing. Consider water is flowing on a converging duct. Okay. So what is the fluid which is flowing means water. So by default it takes as a air. We are going to change it. When I click it, you will get an option called as Fluent database. By default it will be air. So open Fluent database. In that you go for water and save it, copy it first, close it. The air has been changed to water, close it. Now the fluid is water. So don't worry about the solids. Now next you go for cell zone condition. So in cell zone condition, click on surface body because what type of flow it is happening. Click as liquid, apply, close. So what type of fluid we have chosen? We have chosen as water. Next, go for boundary condition. In boundary condition, inlet, interior surface, that is face, outlet, wall. So inlet, what you're going to do is, at inlet, what type of inlet condition it is happening? What is the inlet condition? What is this?
Velocity.
Yes, velocity. So velocity. So I'm going to give the velocity. So as per our diagram, what is the velocity given? 0.002263. 0.002263. This is the velocity. It's an absolute frame. Apply. Close. I have assigned the velocity. At interior surface, don't give anything. Okay. At outlet, it is pressure. It is pressure. As like as per our diagram, it is zero. Just don't change anything. If at all any change in gauge pressure, you can give. At wall, no slip condition. Okay, no slip, stationary wall. It doesn't move. Close. So this is given. So once this is done, go for solution. Go for method, control, report definition, monitoring, residual. Okay, in monitoring, residual plays an important role. So this generally check the convergence. So we're going to change this value. It should be as low as possible so that we get the the problem will converge very fast, which means we will get a very accurate solution. So I'm taking 1 e to the power of 1 e to the power of minus 14. Look at the value, how small value I'm going to assign so that it converges fast. That is the residual we are given. Cell register.
Show
Okay,
it again. Show it once again.
residual. In go for solution monitoring residual. So you're going to give very low value, all the three. So continuing continuity, x velocity, y velocity, continuity equation. It should solve continuity equation. It should solve x velocity. It should solve y velocity.
Take iterations.
I'll tell you. Next, this is just we're going to give the absolute criteria. Should fast
LH.
converge. I'll guarantee.
LHS.
No,
Iterations.
that is the next step we're going to do. Iteration, next step. Okay. So go for installation. When you go for installation, there is called as hybrid installation. Go for installation. It will solve some problem. Now, while running, while run calculation, now you should give the iteration. Okay, how much iteration I'm going to give is I'm going to assign 150 iterations, which means it should take how much iteration? 150 iteration. Now it goes into calculate. Now just observe the figure. What happens? Can you see the convergent? Like I have given that option now. How it is converging. Calculation is done. So the black one, it is called as continuity equation. Red one is x velocity and y velocity. It is converging. Almost we are done with the problem. Last, let us go to plot. Sorry, graphics, contours.
Wait for a minute. Mine is still calculating.
Okay, it takes time, no problem. So once it is done, go to graphics. Once it is converged, go to graphics. There is called as contours. Click on contours. Okay, click on contours. What type of problem it is? Contour of velocity problem. Just click on velocity, save and display, and close. Can you see this? So let me give you the calculated value. See, at outlet, okay, at inlet it is so much 0.00223. At outlet we have found 0.004526. So when I carefully observe, see, at outlet it is almost the same value we got in the range
So
0.05.
to go for graphics.
Yeah, we need to go for graphics,
Okay.
contours, in that contour, velocity contour. So it is almost reaching the nearer value 0.005.
We have to take counter lines.
Residuals, okay. Contours, contour of velocity, save and display. Want to compute what will come? Save and display. You will get a magnitude scale. I think I can able to zoom it. Yeah, I can able to zoom it. Okay, this is a velocity range we have got. At exit it is more. At outlet. So this is the first problem. This is the first problem we have solved. Now let me go to Fluent and check everything it is done except result. Now I'm going to right click. If I update it, the result also it is done. And I can extract online result also. So everything is done. I'll extract the result. Go to file. Sorry. Go to simulate report, online report. If I click generate report, this is additional point which I saw is not necessary. When you have this output, that is sufficient.
Can you repeat once again?
It is running. At last, you like in this dialog box, at last you have an option called as simulate report online. Click that, it will open. Generate report means it takes time to generating. It will give you the output. Okay, but that is not necessary. When you show this, that is more than sufficient. So this is all about the first experiment. Fine.
I don't have that simulate option. Where we have to go? File.
Last option. Okay. I think
Where?
yeah, my system has been hanged because it is simulating.
Okay, 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 okay.
It takes long time.
Okay. And for reports, then
Yeah,
I can.
generate report. Okay. So this is all about the first experiment.
Okay, report. Then I've got options like discrete phase, fluxes, forces, surface integrals, volume integrals.
Yes, all those things we will be getting. Okay.
What I
Fine.
not got the generate report.
Yeah. Okay, fine. Thank you.